You may not have thought about this before, but our nuclei for any given atom can actually spin in three-dimensional space. As it's spinning, depending on where the protons and neutrons are, it might actually generate a magnetic field and it will respond differently to magnetic fields as well. We can take advantage of this to learn a lot about molecules. One of the situations that can happen is that we have an even mass number, which means that either the protons and neutrons added together end up being even, or maybe they're both even. If the protons plus neutrons added together are even, we're always going to have a spin value that's integer. That's actually really hard for us to detect. And if they're both the same, our spin is going to be zero. A great example of this is carbon-12, which makes up most of the carbon in our world. That makes it difficult to measure, but there are lots of other things that we can measure fairly easily. If the number of protons or the number of neutrons is odd, the spin's an integer over 2, and those are actually really easy to measure with a response to a magnetic field. So examples of this include carbon-13, which is about 1% of all the carbon in our universe, or hydrogen, which is almost 100% of all the hydrogen that we have in our world. A spinning nucleus really doesn't make any difference except if we start to apply a magnetic field, because spins will be aligned however they want without a magnet. But as soon as you apply a magnet, you will either align with or against the magnetic field. When you align with the magnetic field, that's going to give you a lower energy state. When you align against the magnetic field, you're going to have a higher energy state. So you see the lower energy states shown in red and the higher energy states shown in blue. We can actually apply stronger and stronger magnets to increase that difference, but with most of our magnets, the change in energy between those states is in the range of radio frequencies. The instrument that we're going to be using today is called a nuclear magnetic resonance spectrophotometer. It's actually very similar to the magnetic resonance imaging that's done in hospitals, and we'll talk about that in a second. NMR, or nuclear magnetic resonance spectroscopy, is going to put our sample in a magnetic field and then pulse it with a number of different frequencies to see what types of things might be changing their alignment with the magnetic field and what their energy is. For any individual atom, it might have a slightly different frequency that it responds to based on its individual environment. And the types of patterns that we see for any individual molecule are the same every time we look at that molecule. The first question we want to ask ourselves is, if we are looking at a spectrum from an NMR machine, how many signals would we see for any individual molecule? Anytime we have an atom that's in the same chemical environment, it would give an identical signal. So one example of that we see at the top molecule. We have 3 things on the top of the molecule that are all labeled HA and 3 things in the bottom that are all labeled HA. Every one of those atoms is attached to either a carbon at the top that's identical to the carbon at the bottom. Those carbons are in the same position around a ring. And so because all of the hydrogens are attached to carbons that are the same as each other, hydrogens are also the same, and they give us one signal. And then we have hydrogens that are attached directly to the ring. Those hydrogens are also identical to each other, and so they give us a different signal. All the hydrogens that give us the exact same signal are called homotopic atoms. Anytime we have atoms that feel distinct chemical environments give us distinct signals. So we see that HA all gives us the same signal and HB gives us the same signal. But when we have HA and HB, those are heterotopic to each other. So we have 2 heterotopic signals. We will always in our NMR see the number of signals that are given as the number of heterotopic atoms, the number of atoms that feel a different environment. So similarly to the example above, the example that's shown down below has a CH3 that's attached to an oxygen that's listed in red or shown in red, and the peak is shown in red as well. That's a different signal than the carbon that's attached to a carbon double bond to oxygen. That carbon is going to shift less, and so we see that signal show up as indicated in green in the spectrum. Now we've talked a little bit about how many signals we'd see. Let's think for a moment about why we might see signals differently. So if you're shining radiation on something, you could experience the full blast of that radiation, or you could wear sunglasses and it would block you a little bit. The same is true for radiation that's felt by these things with electron density around them. We call that shielding. We often indicate the strength of a magnetic field with the letter B. The signal that we get for any individual nucleus, in our case it's going to be protons, will be affected by the magnetic field overall. The magnetic field that each nucleus feels is going to be some combination of the external magnetic field, the B external, and whatever locally is going on around that nucleus, which has to do with its shielding in many cases. So whatever's felt by the actual nucleus will be its actual signal. So here we have shown a line that indicates the external magnetic field. If it encounters an electron cloud around an atom, it can actually generate a current around that electron cloud. Whenever you have a current that's in a cycle, you can actually generate a magnetic field that's in the opposite direction of the magnetic field that induced the current. You'll talk about that a little bit in physics too if you take it. But that means that a nucleus that's at the center of that current, at the center of that electron cloud, can oftentimes feel less of the magnetic field, depending on how much electron cloud density is around it. For any given molecule, we should be able to figure out the number of distinct signals we see, but we should also be able to figure out a little bit about what their environment looks like and figure out where we would expect to see those signals as well. This is actually at the root of magnetic resonance imaging, which is just a medicine applied to NMR. So for example, our fatty acids either show up as saturated for most of the carbons or allylic with protons right next to double bonds. And those two types of peaks tell us about what parts of our body, as we look at an MRI, are made up of fat. Or we might be able to see carbs and proteins show up in a different region. Or we might even see water show up in a different region still. If we look at water and we're trying to figure out where water is showing up in an MRI and it shows up at a much higher concentration inside something that should be mostly carbs, proteins, and fatty acids, that tells us that tissue is damaged. And so we're really using the same type of information, but more limited in MRI as we use here. So for our molecules shown, we can figure out how many different types of peaks there are, which we've done before. Why don't you pause and try to identify how many distinct peaks we would see? So how many different peaks would you expect to see for the molecule of isopropanol or 2-propanol that's shown at the top here? So starting from the left side, we should be able to see these three hydrogens are identical to each other because they're all attached to the same carbon. This carbon is attached to the alcohol carbon, the one that's attached to an oxygen, but so is the carbon on the other side, and it also has three hydrogens. So these carbons are identical to each other, and therefore their hydrogens are all identical to each other as well. But if we look at the hydrogen that's on the central carbon, that carbon's different from the other carbons, and so that hydrogen is also different, as is the hydrogen that's on the oxygen. It's the only hydrogen that's on that oxygen. So we should be able to identify not only how many different hydrogens there are, but also kind of where they are. Hydrogens that aren't close to an electronegative atom tend to show up in a saturated region. So we'd expect our hydrogens that are highlighted in yellow to show up around there. Hydrogens that are attached to an electronegative atom tend to show up much more shifted. And so we see that here. That's actually why carbs show up there, because there are a lot of alcohols and carbohydrates, a lot of OHs. And then we should also be able to see the type of H's that are attached to oxygen. Those, because of hydrogen bonding between molecules, can actually exchange really quickly, and the peaks tend to show up fairly broadly and have a broad range in which they can show up. And so this entire range up here is all places that alcohols could show up, depending on other factors. Anytime we have more protons, we would expect to see more signal, and that is true for all of our proton spectrum. So here we have shown two different peaks. On the leftmost piece, we have the CH3, that's shown in red, and we have an integral trace that shows essentially how much area has been under the curve in that section. So you can see that it's flat and then kind of goes up and then goes flat again. The area between those two blue lines that I just drew show approximately how much relative area we have under just that first peak that corresponds to the CH3. We can look at the next area where it rises, and so again we'd look here to here on the next peak, and we can see that roughly we have three equal sections equal to the same amount that we had for the other peak, which would tell us that we have 3 times as many of those protons. Now, nobody tells you exactly how much they are, they only tell you the ratio. So it's a 3-to-1 ratio, but it's actually 9 to 3 for protons. So we know that we can have different peaks with different integrations, but in some cases, we actually see more peaks than we'd expect for a given molecule. So the molecule shown is bromoethane, CH3CH2Br, meaning that we have a carbon that's attached to 3 hydrogens that's attached to the next carbon, which has 2 hydrogens and a bromine coming off of it. That molecule should only have 2 chemically distinct hydrogen atoms. We'd have 3 hydrogens on the carbon that's farthest from the bromine, and 2 hydrogens on the carbon to which the bromine's attached. We can actually see the integral trace on here, and we can try to figure out which one is 3 and which one's 2. This one right here is going to be about 1.5 times the height of this, indicating a 3:2 ratio. So we see that the carbon that is a CH3 has a higher integration, but we also see it shows up at 3 peaks. And the CH2 actually shows up with more peaks. So all of our signals can be split into more than one peak. That's because every one of our hydrogens is a nucleus that is magnetic. And if we have tiny magnets next to each other, those magnets can change the local environment field, either adding to the overall magnetic field or subtracting from it. And it's more or less statistically distributed. Anytime we have a hydrogen on a carbon next to a hydrogen that we're looking at, that hydrogen as a tiny magnet can actually split nearby. And so we can figure out how many hydrogens are neighbors to the ones that we're looking at based on how many splits we have. If there are no neighbors, no distinct magnets that are affecting the magnetic field, we'd see everything as a singlet, just a single peak that's not split. But for every type of hydrogen that's nearby, everything that will split, we would end up with an additional peak. And so we'd say if we have one neighbor, one coupled proton, one that's nearby, we'd end up with 2 peaks. So we'd have one more peak than the number of neighbors that we have. We'd say it's the n+1 rule. If we have 2 neighbors, we'd see 3 peaks. And if we have 3 neighbors, we'd see 4 peaks, and so on. The ratio of peak integrations that we'd actually see is predictable, as the peaks are going to overlap in the same way that Pascal's triangle is built up. In Pascal's triangle, each new entry is the sum of the 2 values above, with the outermost values always being 1. So if we look at 1 to 2 to 1, we'd say the 1 and the 2 add together to make 3. The 1 to 2 ratio again sums to make 3, and the outermost value is 1. And we can continue that down the triangle. 1 plus 3 is 4, while 3 plus 3 is 6, and so on. We could actually even figure out what the next row would be. The hextet, which is not shown, would be if we have 5, and we would expect a 1 to 5 to 10 to 5, or sorry, 10 to 10 to 5 to 1 ratio. So what does all this have to do with our lab today? If we look at rubbing alcohol, it actually has 2 components, one of which is 2-propanol and the other is water. And we can use what we learned today to detect what types of signals are coming from the 2-propanol and what types of signals are coming from water. I actually have these overlaid with reference spectrum with 2-propanol on the left and water on the right. And so we can see that we have a number of heterotopic protons here and here and here. So we have 4 different signals that we should, or sorry, 3 different signals that we should see. And we should be able to expect how shifted those are, like we had talked about in the slide before. And we should also be able to tell the splitting. So see if you can identify what the splitting is on the green atom, or what the splitting is on the yellow, and use that to identify which peaks are indicated on the spectrum. If we look at water, water doesn't split at all. Water actually in most instruments shows up as a really broad peak. And so this peak right here, which has an H on an O, it's actually really similar to the H on an O that's present in water. And so these peaks will overlap. And so we'll need to use the ratio of peak heights that we'd expect to see to figure out how much of this signal is coming from this molecule and how much of the signal that we'll see in the isopropanol altogether is actually coming from water as well. If we can figure out how much is coming from each, we can figure out overall what the ratio is of 2-propanol to water.